Alright, today we're going to do experiment 10, which is chemical kinetics 1. Now the reaction that we're looking at is our S2O8 - 2, our peroxy disulfate, reacting with our iodide ion and producing our sulfate and our triiodide ion. Alright, so that is the reaction that we are studying. Now to study this, we are going to add the S2O3 - 2, which is our thiosulfate. It reacts with our triiodide ion very, very quickly. So as soon as our triiodide reaction, as soon as our first reaction forms triiodide, it reacts immediately with our thiosulfate. Now once we run out of our thiosulfate, which is how we're going to determine the rate of this reaction, the starch that we add is going to react with our triiodide ion, and it's going to turn into a dark blue complex, and that will indicate that we are out of S2O3 - 2, and so that's how we will determine our rate. So again, when the S2O3 - 2 has a concentration of 0, the triiodide will then react with the starch, it will turn blue, and we will stop our clock, and we will then have our time that we will record in seconds for this to change colors. So this is called the iodine clock reaction. It's a very famous chemical reaction. All right, and so when we are calculating the rate, we are going to calculate it by the disappearance of our S2O3 - 2 divided by 2 delta T. All right, so we will have our S2O3 concentration, and so we will take the change in that, so that is the final minus initial. The final concentration is 0. That's when it will turn blue. The initial concentration we will have to calculate. And then our delta T is the time that it took to change colors in seconds. Now once we have our rate, we go to our rate law, and the rate law is rate is equal to K times the concentration of our reactants. Our reactants are the iodide ion raised to some power X that we have to find experimentally, and that's the experiment we are running today, times the S2O8 - 2 raised to some power Y, which must be determined experimentally. Again, that's what we are doing today. So our two reactants, we are going to change our concentrations. So if you read along in experiment 10, you see that in run 1, we're going to use 0.2 molar Ki and 0.1 molar of the S2O8 - 2. In run 2, we add 0.1 molar of each one. And in the third one, 0.1 molar of our I- and 0.050 molar of the S2O8 - 2. All right, so in general, when you have a lower concentration, the reaction should take longer. And so the first reaction should be the fastest, second reaction the next fastest, and third reaction should be the slowest reaction, if our concentrations have a determination in our rate law. All right, so it also asks for our stock solutions, and so on your data sheet you have stock solution for Na2S2O3, and I will show you the bottles of these. The first one, the S2O3, is 0.0059 molar. The S2O8 - 2, the stock solution, the bottle that is given, is 0.10 molar, and the Ki stock solution is 0.20 molar. And then there's also going to be a starch given, and that is an indicator, so we do not need a concentration for that. We're adding the starch so that it will react with the I3- and turn blue, and we will know when to stop our reactions. Now the volumes that we're going to use for each one of these runs, for the S2O3 - 2, we're going to have 5 mils every time. S2O8 - 2, 5 mils every time. The I- 5 mils every time, and then the starch, we're going to use 3 mils every time. So our total volume in our flask is going to be 18 milliliters. And this is going to be important when we do our calculations, because in our calculations it says use the diluted concentrations. So once you've added 0.0059 and you start adding 5 mils of something else, 5 mils of something else, 3 mils of something else, now you have a lower concentration. You are then diluting it, and we will have to calculate what our concentration is after we've added all four things. All right, so now we're ready to go start our experiment. And so our stock solutions. So here we have our starch. Next to that is our S2O3 minus 2, and that has a concentration of 0.0059. The next one is our Ki, 0.20 molar Ki stock solution. We're also going to use 0.2 molar KNO3 in order to make our 0.1 molar Ki solution. So stock solution is 0.2. On the board you see we also need 0.1. We are going to make that using our KNO3. And over here we have our stock solution of our S2O8, which is 0.1 molar. And then behind that is our sulfate, which is also 0.1 molar, which we're going to use to make our 0.050 molar S2O8 minus 2. All right, so let's start our reaction. Let's see. All right. Yes, here I am. Okay. Hello. Here I am. All right. So we are going to start doing the reaction. So we will start with run 1, which is using our stock solutions. And we cannot mix our solutions until they are in our reaction flask. And so we're going to have our starch. Then we're going to have our S2O3 minus 2. Then we're going to have our Ki. And then we're going to start the reaction by adding our S2O8 minus 2. And that's when we will start our timer. All right. So first thing we have to do is put in 3 mils of starch. Okay. Then we're going to put in 5 mils of our S2O3. All right, and then 5 mils of our Ki. Right, and then we're going to start the reaction with our S2O8. So we need 5 mils of that. And we'll put, in this graduated cylinder. All right, so we take then our reaction vessel here, and we're going to add our 3 mils of starch. We're going to add our 5 mils of S2O3. We're going to add our 5 mils of Ki. All right, so this is when you get out your stopwatch. All right, so we have our stopwatch. You will be doing this at home. All right, and I'm going to time one of these, and then you will time the rest of them. All right, and so usually you'll have a another set of hands. One person pours it in, one person pushes the button. So I'm going to pour it in, and I'm going to push the button, and I'm going to stir it, and then I'm going to let it set. All right, and now we are waiting for that to turn to the blue color. Now, while we're waiting for that, I'm going to set up for our next reaction. And our next reaction is using 0.1 molar Ki. So instead of the 0.2 molar Ki, we're going to add 0.1 molar Ki. And to make this, it tells you in the directions, you're going to add 10 mils of 0.2 molar Ki and 10 mils of 0.2 molar KNO3. And so I did that, and I have my solution here. So I'm going to set up this while we monitor our reaction there. And so we will have the next reaction going right when that turns blue. I'm doing the same thing, 3 mils starch, 5 mils of each of the others. Oh, and it turned blue. All right, so there is the blue color right there. And so I got 1 minute and 46 seconds. It was probably more like 45 seconds. But there is the dark blue color that we're looking for. All right, so we have run 1. Now we know that run 2 has a smaller concentration of the Ki. So it could be the same amount of time, but most likely it's going to take longer this time for it to turn the dark blue color. Now when I'm adding my Ki, since I'm changing the concentration, it is not 0.2 molar, it's 0.1 molar. What I'm going to do is I'm going to thrice rinse my graduated cylinder to make sure that there's no 0.2 molar in there. I don't want 0.2 molar, I want 0.1 molar. And so I will thrice rinse the graduated cylinder, then I will add my 5 mils. All right, we had a bit of a camera problem there. Right now we are doing run 2 with the 0.1 molar of the S2O8. So run 1, it took 1 minute and 46 seconds. All right, run 2, I will tell you the time since we had some camera problems. I will tell you what that is. All right, so while this is going, we're in 1 minute and 13 seconds right now. We're going to let that go. I'm going to prepare for run 3. Three mils of starch. Five mils of the S2O3. 0.1 molar Ki again, so I don't need to thrice rinse this. It is again 0.1 molar Ki.
All right, but this time we're going to add 0.05 molar of the S2O8. So we're changing the concentration of the S2O8. So I will thrice rinse. Make sure it's not the 0.1 molar. If it's wet, it's going to be wet with the 0.05 molar. And to make that, that was in the directions. You added 10 mils of the 0.1 molar S2O8 with 10 mils of the 0.1 molar sulfate. Oh, and we are blue. All right, and so that, not sure how much I missed it by, but we are at 3 minutes and 8 seconds. 3 minutes and 8 seconds. All right, so now I'm going to put the 5 mils in here. All right, and then for our third run, we're putting in 3 mils of starch. Five mils of the S2O3. 5 mils of the 0.1 molar Ki. And then to start it, we add the 5 mils of now 0.050 molar of our S2O8. This starts it. Pour it in, push go, give it a swirl, and we wait for that to turn blue. All right, so now for our next run, we're going to do an unknown Ki. And our unknown Ki is right here, and we have unknown Ki number 3 is what we're going to use. All right, so while this is going, I'm going to prepare the next one. Now what we're going to do is we're going to have our starch, we're going to have our S2O3, and this time we're going to use our unknown concentration of Ki. Again, we're going to use 5 mils. Again, we're going to thrice rinse it to make sure that all the 0.1 is gone. Whatever our unknown concentration is, that is what we're going to get for that. So 3 mils of starch. Of the S2O3. All right, then our unknown Ki, I'm going to thrice rinse 0.1 molar out. And add 5 mils of our unknown Ki. and for the unknown, I would rather it go faster than slower, so I'm going to go back to the 0.1 molar of the S2O8. You could use either concentration. I'm going to use the 0.1 molar S2O8. So I'm thrice rinsing out the 0.05 molar. And then I'll fill it with 5 mils of our S2O8. Alright, so all we have to do is wait for our run 3 to turn the blue, and while we're waiting here, I will mix these. Alright, we are still watching our solution. Alright, there it goes. Turning blue, we will stop it. So there is our blue color, and that took 5 minutes and 21 seconds. Alright, and now we will grab another reaction vessel. All right, we're going to take our 3 mils of starch. We're going to take our 5 mils of our S2O3. All right, so starch and S2O3 have not changed. They were the same each time. And this time we have our unknown Ki, unknown number 3, Ki. And so again, we're going to start this with our S2O8. We're using 0.1 molar S2O8. And so I'm going to reset that. And I'm going to pour it in. I'm going to push go. I'm going to give it a swirl. I'm going to let it set and wait until it turns blue. And for our unknown, there are 2 runs in some of the experiments. We're just going to do it one time. Again, you're not going to be graded on the correct answer. It is just going to be graded on the calculation to find the concentration of your Ki in this unknown solution. All right, but then next we're going to do the effects of a catalyst. So I will get this going again, my 3 mils of starch. My 5 mils of S2O3. I'm going back to the 0.2 molar Ki, so I'm going to thrice rinse it. Alright, and it turned blue. So that took 3 minutes and 21 seconds. Alright, so now we're going to do the effects of a catalyst. So have another, set this. Okay, so for the catalyst, we're going to use a copper nitrate catalyst. And so a catalyst works by lowering the energy of activation and makes the reaction go much faster. So we are going to put in our same things. We're going to put our 3 mils of starch, 5 mils of the S2O3. Now we're going to do the same as the first 3 runs, so I'm back to my 0.2 molar Ki, so run 1 was 0.2 molar Ki. Now before I add the S2O8, I'm going to add a drop or 2 of catalyst. Alright, and so now when I pour this in, you see that it takes 2 seconds. Alright, so the reaction is very, very fast. Let's try that again. Alright, 3 mils of starch. S2O3, 5 mils of that. Alright, Ki. Alright, so this time we're going to use the thrice rinsed once, twice, thrice rinse. Okay, 5 mils of this. Here. S2O8. Alright, so this time, I got my reaction vessel, put in the starch, put in the S2O3, put in the Ki, put in a drop of the catalyst, and then add the S2O8, give it a swirl, and set the timer. And that is 30 seconds for, so we're going to go with 30 seconds on the second one. So go with 2 seconds on the first one, 30 seconds on the second one, and then our last reaction for experiment 10. 3 mils of starch, five mils of the S2O3, five mils of the 0.1 molar Ki, and 5 mils of the 0.1 molar S2O8. Reaction vessel, and the starch, S2O3, Ki. Alright, drop of catalyst, and the S2O8, and we time it. And that is 25 seconds. So 2 seconds, 30 seconds, 25 seconds. So for the catalyst, it was just to show that these reactions are much faster when you add a catalyst to the reaction mixture. And so that is it for our data sheet. We will go through the calculations next.
All right, here are the calculations for experiment 10. Chemical Kinetics 1. Now remember, all calculations, your concentrations must be after mixing. So all concentrations after mixing means that we have to do MV is equal to MV. For your S2O3 minus 2, the stock solution was 0.0059 molar. So each time we ran the reaction, it was 3 mils, 5 mils, 5 mils, and 5 mils. And so the total is 18 milliliters. So we take our 0.0059 times our 5 mils, and that's equal to the molarity times the 18 mils. So divide both sides by 18. Every time you're using the S2O3 minus 2, we're going to use 0.0016 molar because that is the concentration after mixing. All right, so for your S2O8 minus 2, the stock solution was 0.1 molar. MV is equal to MV. So each time we took 0.1 molar of the S2O8, we used 5 mils of that. And we added that to a total volume of 18s. And so your S2O8 minus 2, your 0.1 molar, after mixing is 0.028 molar. For your I minus, the stock solution was 0.2. Then after mixing, you took your 0.2 molar, 5 mils of that. What is it now that it's 18 milliliters? Your I minus concentration is 0.056 molar after mixing. So the rate law that we are determining from this lab is rate is equal to K, your I minus concentration raised to the X power, your S2O8 minus 2 concentration raised to the Y power. Alright, so the first thing that we come to in our calculations is to calculate the reaction rate. And so it was shown before in the pre-lab that the rate is equal to the disappearance of S2O3 minus 2 over 2 times the change in time. I'm going to do the calculations for run 1. Alright, and so your rate is equal to your change in concentration of S2O3. The final concentration is 0. The initial concentration we just calculated after mixing, 0.0016. Divided by 2 times delta T. Now your delta T is going to be in seconds. So for run 1, our time of color change took 106 seconds. And so when we calculate that, we get a rate of 7.5 times 10 to the minus 6 molarity per second. You will then repeat that calculation different times for different color changes for experiments for runs 2 and 3. Alright, and so you will have all of your rates. Now we're going to do the next part, which is the ratio of rates. So you simply divide what you got for rate 1 divided by rate 2. I did not round any numbers and I got 1.8. If you do it a different way, you will get 1.7. Again, the error is always in the last number given. The way I did it, it was 1.8. If you take the ratios of rate 2 and 3, either way you do it, you're going to get 1.7. So you need to show your work on how to get those ratios. And make sure you give the correct sig figs and the correct rounding. Alright, so reaction order for I minus. So we're going to take rate 1 divided by rate 2. We already calculated that above. That was 1.8. Then we're going to take K1, concentration of I minus from run 1, raised to the X. The S2O8 minus 2, raised to the Y for run 1. Divide that by the rate 2 law. So that is the rate constant K for run 2. The I minus concentration raised to the X of run 2. The S2O8 minus 2 raised to the Y of run 2. Alright, so the rate 1 divided by rate 2, we have that. That's 1.8. Now the rate constant is exactly that. It is a constant. We did not change the temperature, and so the only thing that can change our rate constant is changing the temperature. So K1 and K2 are both constants, the same numbers, and so they cancel out. Your I minus concentration in run 1, it was 0.056. In run 2, it was a different concentration. It was 0.028. When we look at our S2O8 for run 1 and run 2, we did not change our concentration of S2O8. And so the concentration in the numerator and the denominator are exactly the same, and they cancel out. And so you are left with 1.8 is equal to 0.056 to the X divided by 0.028 to the X. And using our exponent rules, we come out with 1.8 is equal to 2.0 to the X. So in order to solve that for X, we take the log of both sides. You can take the regular log log or the natural log, it doesn't matter. I used log log. So I took the log of both sides, and I also know my log rules. So you have to know your log rules. When you have the log of 2.0 raised to the x, you bring the x out in front, and it becomes x log 2.0. So you end up with log of 1.8 is equal to x log 2.0. To solve for x, you divide both sides by the log of 2.0. And when you divide both sides by the log of 2.0, you get x is equal to 0.78. And on your data sheet it says to round to the nearest integer. And so that nearest integer is 1. And so our x is 1. And so it is first order with respect to our I minus. You will do the exact same thing for the S208 minus 2. And you will get y is equal to 1. You have to show all your work. Just like we did for finding x, you will have to find y, and it will round to the nearest integer, and that will also be a 1. And so the correct rate law for this reaction is rate is equal to k, I minus raised to the first, S208 minus 2 raised to the first. So the next part we come to is to calculate the rate constant k. I will show it for run 1. To find the rate constant for run 1, we take our rate, which we calculated as 7.5 times 10 to the minus 6 molarity per second. And that's equal to our rate constant K of run 1 times the concentration of I minus, which was 0.056 raised to the first for run 1, and 0.028 was our concentration of the S208 minus 2 for run 1. And so when we divide both sides by 0.056 and 0.028, we solve for k. K is 4.8 times 10 to the minus 3, 1 over molarity times seconds. And so you will do that exact same calculation to find K2 and then to find K3. And I did that. You will have to do that and show your work. And I did that in order to get the average. And so the average that I calculated is 5.6 times 10 to the minus 3, 1 over molarity times second. So now we're ready to calculate our concentration of I minus in the unknown. And so now we have, again, our rate law, and we have our calculation of rate. And so to calculate the rate, we have to put, just like we did before, we put in our numbers for the unknown, and the rate is 4.0 times 10 to the minus 6 molarity per second. For the K value, we're going to use our average K value, which is 5.6 times 10 to the minus 3, 1 over molarity times second. The I minus concentration, that is unknown. We are calculating that. And for the unknown, we use the stock solution of our S208, which after mixing is 0.028 molar. So when we divide both sides by the 5.6 times 10 to the minus 3 and the 0.028 molar, we get I minus concentration is 0.025 molar. Now that is the diluted I minus concentration. That is the 18 milliliter concentration of I minus. Now you're going to have to use MV is equal to MV to get the undiluted concentration of your I minus. So we have the 18 mil concentration. We want the 5 mil concentration. That would have been our stock solution of our I minus. We took our stock solution and we had to change it to the diluted. Now we're going to take the diluted and go to what does the bottle say for this concentration of I minus. And we are not going to do any calculations with the catalyst. The only thing we need to know about the catalyst is it speeds up the reaction by lowering the energy of activation.